Thanks for coming to learn more about CockroachDB. And Cockroach is an open source, distributed, scalable SQL database that can survive failures. I think that within just the next few years, we're going to see databases like Cockroach actually become a very standard and accepted way of building new applications that need to scale. So this is important stuff. Our presenter today is Tamir Duberstein. And he's been at Cockroach Labs for over 2 years now. And probably a lot of you remember him as actually being an engineer here at Square, because he was an engineer here at Square before that. And you probably have some memories of him fixing and migrating Square Web. And so we all benefit from all the work that he did as a Square. And so without further ado, I'm going to turn the time over to Tamir.
Thanks, Andy. Cool, yeah, so thanks everybody for coming. So thanks for the intro, Andy. This is meant to be a pretty casual talk, so if you have questions at any point, sort of, just raise your hand or maybe even interject, whatever you feel comfortable doing. Unfortunately, I'm going to have to stand like mostly over here, but hopefully it's not too much of a jarring thing. So yeah, so let's just jump right in. So why did we do Cockroach? So to understand that, it's just a quick history of databases. So we used to have, Square is big on SQL. You guys probably know that Square went through an evolution from MySQL to Postgres, back to MySQL, and then a little bit later came some NoSQL database. I think BMO was on like HBase and whatever. And hopefully everyone here knows about the trade-offs, but in case you don't, the benefits of SQL databases, they give you transactionality, they give you indexes, so you can declare that you want the database to maintain some secondary ways to access your data, and it will take care of it for you. But it doesn't scale particularly well. And the flip side of that is some of these NoSQL systems that scale better, have better availability properties, but they trade away some of those, some of the nice benefits of SQL. So like I said, some of the limitations are some scale with SQL, fault tolerance. We'll talk about that a little bit more detail later. No transactions in NoSQL databases. You got to do your own indexes, and of course, if you assume that you'll get consistency, you probably won't. So that's sort of the impetus for Cockroach. And so the goals are, like Andy said, to be scalable, survivable, strong consistency, so you don't lose any of those guarantees that make your life easier as a developer, and then SQL just so that it's easier to use, and of course open source because it's very hard to get people to use your thing unless it's open source. So sort of high level agenda. I want to so the goal of the talk is to give you guys a base understanding of how the system is architected, what are some of the design choices that we made, so that you can have some intuition about how the system will behave under different circumstances. So to get there, we'll talk about the high level architecture, how we distribute data, how it's replicated, how transactions are implemented at a very high level, and then how we map sort of our KV underlying thing to sort of how do we bolt on SQL onto this KV thing, and then some deployment, and we'll talk about like where the product is right now and what you shouldn't do for it. Cool. So any questions so far? Great. So the architecture, to the extent that we're going to talk about it, is just a sort of a stack of abstractions, and this is kind of a reminder of our agenda. So we're not going to talk about storage. This is not particularly interesting for understanding how the system behaves, but we'll talk about those guys, replication, distribution, up to SQL, and the point is that in practice, the system is actually pretty well abstracted. So SQL doesn't really know much about the KV layer. It certainly doesn't know anything about replication, and so that makes it a little bit more palatable to develop the system. And then also we have future plans to expose maybe other types of databases on top of the same transactional base. So that makes it pretty easy to replace that top brick with something else. There you go. Cool. So data distribution. So what do I mean by that? So when you design a distributed system in general, you kind of have to answer those two questions. What chunks do you break the data into? How big are they? And given that you need to respond to some user query, how do you locate a particular piece of data? And so generally the two solutions to this problem are either a hashing scheme or an order preserving scheme. And does anyone like know what I mean by those two? Okay, so hashing means like if a user wants a key, let's say the key is foo. You pass it through some algorithm, and the algorithm spits out foo is on shard 10. And then you can just, okay, I know where shard 10 is. I'm going to go ask shard 10 for the value of key foo. An order preserving scheme is one where, but the thing is, then if the user asks for the key foo followed by a 0, which maybe is the sort of next logical key, it may be on a different shard altogether. In fact, that's usually a desired property of systems that use hashing to locate data. Order preserving has the benefit of being able to preserve order so that those two keys are adjacent. And so that's what Cockroach is. And so the reason we do that is because we actually want those efficient scans. We very often in SQL workloads want to do something like aggregation. We want to scan over data sequentially, and we don't want to be bouncing around to all the different shards when we do that. Does that make sense? Yeah. Cool.
What's the notion of adjacency here? Is it in some key space or?
It's lexicographic. However, it's lexicographic at the key value level, but then when we encode the SQL keys, we make special arrangements to make things that we want to be adjacent actually encode as adjacent. We'll talk about the anatomy, how keys get encoded in SQL at the end toward the end of the topic.
But from the application development perspective, it's really the higher level, like what adjacency means at the higher levels that matters to us, right?
Right. So at the higher level, it means that adjacent rows in the table are very likely to be adjacent in storage.
Right. And how about like cross table, for example? Spanner, for example, provides provisions so that there's a notion of adjacency that generalizes passages of the table.
Right. So I think Spanner, what you're talking about is inter-leaf tables in Spanner.
Yes.
Yeah, we have the same. Okay. Yeah. So you can probably going to be a little bit easier to talk about that if we circle back to it at the end. Cool. Sure. Okay. So right. So order preserving has the benefit that you can sort of, once you get down to the key, you can sort of go to the next key very easily. But the downside is that you can't, like when the user asks you for the key foo, how do you locate that key? Well, you can't just hash the key and figure out where it is. So you need an additional index structure. And so sort of the illustration I just gave, so that this would be our key space. So those are our shards, and you'll see that these keys are all sorted. So we arrange for them to be sorted, and sort of they maintain that order, which makes it easy to do sequential things. But like I said, we need an indexing structure. So in Cockroach, we actually have what we call the meta records, which are sort of located on a special group of, they're contained in a special range. And so whenever you ask for the key foo, the first thing we need to do is find the meta records, which are always located essentially in the same place. And those will tell us where the shard is that contains the key that we want, which is free to float around the system, and the index structure will be updated to sort of reflect that. Does that make sense? Cool. So like I said, the benefit though is if you wanted to do that kind of a SQL query, which let's pretend for the moment that it maps to this very nice sort of key value layout, we can just hit and do sort of the minimum, relatively small set of shards. Maybe not optimal if they happen to be arranged a little bit differently, but pretty close. Cool. So the way that things work in Cockroach is as you sort of insert data, these shards have a tendency to grow. And for reasons that we'll sort of come back to, we sometimes want to split them so that they can move around the system independently. So that's exactly what happens. At some point, the shard gets too big, we split it, and then we amend the shard index to reflect that reality that now this data may be elsewhere. Cool. Any questions on that?
So like, how does, I guess, so you're saying you split when a shard is too large. Like what kind of like notion of balancedness is the system looking for? Like how is it trying to sort of like decide when to split shards and how to split them?
Sure. Currently splitting is based just on size. We'll get to that too, but when a shard is 64 megabytes, we just chop it in half. We look for something near the midpoint, but then we pay attention not to split in the middle of a SQL row. In the future, you can imagine that if you have a key that's very hot, it may actually want to be on its own shard, and the system may take that into account. But that's not currently the case. Cool. Question back then.
Does write contention ever happen on the meta index in practice? Every write has to.
Yeah. So in general, contention in Cockroach is on a per key basis. So in order for there to be contention on the index would imply that there are multiple changes to the same entry in that index, which is very unlikely. It's possible, but it's very unlikely. It's also the case that those kinds of splits aren't happening like very, very frequently.
Yeah.
Compared to other kinds of traffic. Like there's definitely problems under contention in Cockroach in that transaction model, but this is not where that comes through yet. Okay, cool. Yeah.
What sort of downtime is there for when splitting's happening?
You mean like what kind of
Like are queries affected when, let's say,
when splits happen?
Yeah.
Think about that. Let's circle back to it, and then once you guys have an understanding, we can all just kind of reason through it. That's all I'm doing. Okay. All right. So let's talk about placement. So what does data actually look like in the cluster? So pretending that we have 3 nodes, and by default we replicate. So ranges are what we call those shards in Cockroach. So pretending that we have 3 nodes and we have the default settings, every range will be replicated 3 times. And so every node will have 1 replica of each of those ranges. And what happens when the system is perturbed by adding a new node is that the system will notice that there's one node that has a bunch of free space compared to the other nodes, because it's actually looking for balancedness in terms of disk utilization, at least at the moment. And so it will up-replicate one of those ranges to that new node. Eventually, it will sort of down-replicate one of those old replicas, and then there's a background thing that comes around and eventually actually deletes that data. Cool. And of course, this process continues until the system is like roughly balanced. Cool. And then let's say we lose one of those nodes, so that guy goes away, and now we have a couple ranges, all but range 2 that is under-replicated. So exactly what you expect will happen. Data is replicated back again, and then after some period of time, that old that lost replica is forgotten, or the lost node is forgotten and the replicas are forgotten. So if that node now, let's say it's being restarted or something, or it had a network partition or something, we lost it, then it comes back, the system will treat it as a blank node, and those replicas that are still on it will be hit by that same background process and just deleted. And yeah, we can't reuse that data after that has happened. Cool. Yeah. So like I said, ranges are roughly 64 megs, or at least that's the threshold when we sort of split them. The trade-off between the size of the range and sort of the trade-off between being large and being small. So if it's small, it means you can easily replicate it around. But remember that we have that one range that is very special and contains the indexing structure. So because we can't split that thing, that indexing structure, the size of the range for that indexing structure actually dictates how much data is addressable by the system, right? So if you take like the average size of a index entry and divide the size of a range by that, that's how many ranges you can address, multiplied by the size of a range is how much data you can address in the system. What I didn't tell you is that indexing structure in Cockroach is actually bi-level, so there's a exponent there. So I think if we assume that every range is, I can't remember if it's 64 or 32, it ends up being like 4 exabytes is how much data you can store in Cockroach before you run out of indexing structure. And then of course you could jack up the size of that range. Yeah. Obviously, if they're large, then you have a problem moving them around, because now you have to like pass on the network the entire range before that new replica can participate in meaningful projects. And the size is I think probably stolen verbatim from Colossus, where a bunch of the guys on the team worked from Google. Cool. Cool. Any questions on that?
So why do you want the size of the meta ranges to be the same as the regular ranges?
They don't have to be. It's a configurable thing, so you can change it. But they do suffer the same problem that if you lose a machine that happens to be holding the meta ranges, you need to like up-replicate the meta ranges, right? So there is potentially a period of reduced availability until that happens. So if you made that thing like a gig, then you're waiting, you're running at reduced availability until that replication happens.
About the availability of the node, if there's a network connection issue with the node, where it says a blip, then does that mean that that node got dumped? When the node got wake up again, all the data needs to be wiped and reconstructed.
Yeah, that's a good question. So currently it's a hard-coded time threshold. So if a node goes away and we don't see it for 5 minutes, then we forget it.
Okay.
So blips typically won't just cause nodes to get wiped unnecessarily. Yeah.
Okay.
But it's a heuristic. You can imagine that you might want that to be more intelligent in the future. Also. Yeah. So.
What's the orchestrating agent in that process? Because if you have two nodes and you have a network partition, how do you know which one is the one that's going to delete itself?
Well, if you have two nodes and you have a partition, nothing will happen because neither one of them will make progress. So we'll get to that in the next bit, but the whole thing is built on consensus. So if your total consensus group size is 2, you always need both to make any progress. So they'll both do nothing, and you'll be down basically until that partition heals.
And neither will decide to delete the data?
No, because doing that operation, that replication operation, is itself a consensus operation. It's called a configuration change.
Okay.
So you can't even do that. That won't even go through.
One question. So we're talking about replication here. So is the assumption that there's not a network file system underneath?
There is not a network file system underneath. Yes. Yeah. So we'll get to that in the part where we're talking about deployment, but there are 0 external dependencies. So you just like take Cockroach and run it on some hardware in the cloud where you can decide if you want ephemeral disks or not. Of course, you pay for performance if you have persistent stuff. And yeah, there's no distributed file system, which is very much common expand.
Also, one minor point is that I was under the impression, at least for Spanner, that typical spans could be a few gigabytes in size, but I haven't found any authoritative documentation. So if you happen to know 64 bytes,
That my information may be just as stale as yours. I'm not sure. Cool. So yeah, so let's move on. So yeah, let's talk about consensus and all that fun stuff. So the goal basically for this kind of data replication in general is that we want to be able to tolerate failure. So the typical scheme that is used here at Square, for example. I know there's a bunch of MySQLs that are master, right? That's essentially primary, secondary replication. And then there's consensus, which we'll talk about in some detail. So yeah, primary, secondary, pretty simple. The client sends some command. As soon as it hits the primary and the primary commits, the client gets the ACK, and the client sort of moves on with life, assuming that data has been written. And then the secondary, at some time later, usually gets the same command and propagates that same change. Of course, usually it's not that simple. So if you have a synchronous replication between the primary and the secondary, you can imagine you'll have stale reads. So for instance, the client sends that put cherry to the primary, and then the primary goes down. The secondary never got that right, and now the client queries for it and doesn't see it because there's been a failover and you've lost data, right? No bueno. If it's synchronous, then you suffer low availability. You lose your secondary, like your availability is only as good as the sort of set union of the availability of both primary and secondary. So also not great. And then usually you need a third party to arbitrate that failover. So you like wake up a human, they like need to make a call. Well, do I lose data or like what? Do I try to bring the thing back? It sucks. So really we want all that stuff to be sort of handled without operator intervention. So what do we do with consensus? So we typically have 3 replicas, and the commit only happens, and when I say commit, I mean the client only gets the acknowledgement once a quorum of nodes have written the data. And in this case, quorum is a simple majority. So if you're running 3 nodes, you need 2. If you're running 5, you need 3. And yeah, so Cockroach works this way, Zookeeper, etcd, and all these other ones. Pretty common. Yeah, so what does that actually look like? So in Cockroach, it's actually Raft, which is a leader-based consensus algorithm. So assuming that the system is already running in some steady state, there's a leader, a couple followers. Client says, put cherry, and then the leader will send that off to its followers. And then as soon as one of those followers acknowledges that operation, the client can sort of, the leader and the follower can both commit, and the client can get the acknowledgement and sort of move on. And it doesn't matter if this guy's a little behind, like, it'll catch up. Yeah, so there's the ACK and back to the client. So if we have a failure, what happens? So we try to do the same operation, and then we lose the leader. So the client has now has not gotten the acknowledgement on that write, and then the client comes back and tries to read that same thing. There's now a new leader in place, and that's our follower that was the previous leader, which happened to have written that bit of data. The query will go through the leader, and because a quorum of nodes disagree on the presence of this data, the client will get a not found response. Cool. This is like very conceptual and not actually how the mechanics of this work, but hopefully it illustrates the point.
Sorry, maybe I misunderstood. Did we just lose the value cherry? I thought we had written it because it's acknowledged by.
The client never got the acknowledgement. So the client would have seen something like a broken connection or something. So the client never got the okay back.
But both the leader and the follower had sort of said yes, right?
That was the previous example. So
okay, sorry.
So here's this one.
Yep.
All good?
Yep.
Right. And then the same example, but now we've lost that leader that was the recipient of that. Maybe we just lost the network connection between the client and that leader that the client was talking to. So before the command could complete.
Okay. So these are totally different situations from like the last one. Right?
Yes. Cool. Any questions on that? Okay. Cool. Right. So some observations on what we get from using a consensus algorithm. So the fact that we use Raft to do this kind of thing, it gives us sort of atomic operations on a single key, right? It means that if the client did something that manipulated a single key on a single range, that can be atomic and either like it's all or nothing, right? It either succeeds or it doesn't. There's no case where, depending on which replica you later attempt to read from, you may get different results. So that's great. But what it doesn't get us is atomic operations across multiple keys that may reside on different ranges, right? And that's basically a transaction. So so how do we do transaction? So just a quick sort of refresher on what transactions means. Again, you want all or nothing semantics. So you don't want you don't want transactions to interleave one another. If there's two transactions in progress, one of them's not yet committed, it shouldn't be possible for the other one to observe whatever this other guy is doing until he's committed or aborted. For people who know about isolation levels, Cockroach by default is serializable, which is sort of the highest isolation level you can get with most sort of traditional databases. I think MySQL is the highest one that you'll get. But we also support snapshot isolation, which is slightly weaker, but can have better performance if you're really sure that's what you want.
Linearizability or external consistency.
Right. So you're asking in contrast to Spanner.
Yes.
So Spanner is linearizable. Cockroach is not linearizable. So it is linearizable for transactions which overlap in the key space. So if you have two transactions that share at least one key, then it will be linearizable.
Okay.
Otherwise, it's serializable. So if people are interested, we can sort of give a concrete example on when that matters, sort of toward the end. Cool. So how do transactions actually work in like MySQL or Postgres or something like that? You basically those systems will, the first thing they'll do is they'll use some durable storage to write a record indicating that the transaction has begun. And then they'll sort of log whatever mutations they intend to perform. And finally, write a commit, and sort of that marks all of those operations as having been applied. Does that make sense? So that way you bootstrap this multi-key atomicity on the atomicity of a single key. The final state of that record, whether it's committed or not, determines whether the entire transaction was committed or not. Make sense? So it turns out we do like something really similar in Cockroach. So we basically do the exact same thing. So we write to a range, we write a transaction record, which has some sort of metadata, and then we sort of go off and do things on other ranges, and eventually come back and sort of tie those mutations to the transaction that's going on, the transaction ID, and eventually we come back to that transaction record and mark it either aborted or committed. So I'll show what that actually looks like. So we're starting a transaction, we do a begin, and there's a transaction record created somewhere on some range in the system. And then we do a put, and so that TXN1 thing is basically, that is a write intent. So it's not a proper value. It's not the same as those two other keys. It's a special key that indicates that it's not yet fully written. It's part of an ongoing transaction, and it has the transaction ID attached to it so that you could look up the transaction record if you. And then we do another put, same thing. And finally, we go back and mark that transaction record committed. And at this point, the transaction is committed, meaning that any future readers encountering these values will be able to determine that those are proper values and they should be read. And then there's like an asynchronous thing that goes by and cleans up those intents and makes them into proper values. Right? That make sense?
So in like the interim where the write intent is still there,
yeah,
you basically have to consult the transaction record.
Right. So
right.
So if there's a race where the cleanup hasn't happened yet and some reader comes along, it will consult and it will actually resolve the intent since it's already there.
So it's just there's like a period where like access on those keys is a little bit slower, I guess.
Yep.
Basically just two-phase commit across them, or is it?
Right. I mean, essentially, yeah. Yeah. There is an optimization where if everything you're doing happens to be on the same range, it's one phase commit and there's no transaction record. It just all happens
In the same range or on the same server?
No, on the same range, which is, well, yeah, no, not on the same server. It's also exceedingly unlikely that you're doing something, or at the moment, the system doesn't arrange for runs of ranges to be on the same sets of servers. Right? If you did arrange that, then you would benefit from being able to do one phase commit across multiple ranges. Currently, we don't do that, and also the way that we process operations is sort of each range is concurrent, so there's no synchronization between them.
This could potentially be a major scalability bottleneck, given that your chunk sizes are relatively small, right? So if you have transactions that would normally span a larger space, like you might frequently have in MySQL, where the transaction domain is actually like hundreds of gigabytes, then this could radically drive up the cost due to very wide.
Yes, because the transaction domain is hundreds of gigabytes. It is 100%, it's virtually a guarantee that the data will not be co-located, first of all, and second of all, since we don't do this optimization anyhow, yeah, you would observe that. But again, if you're doing something like that, you're not using an interleave table somewhere that you probably should be. Okay, it's hard to answer that without knowing what the workload is. Cool beans. Okay, so what happens when there's a conflict? So what I just showed, that's like a really simple case. No conflicts, just one transaction doing its thing. So let's show a conflict example. So this will be a read conflict. So the first transaction comes along, writes its intent, and the second transaction tries to read that same key. And because that intent is still not a proper value, it figures out that it needs to consult the transaction record, which is still pending. And it's going to ignore that intent, right? So this is actually not 100% true. In Cockroach, everything has a timestamp attached, and so this is the case if the transaction 2 timestamp is lower than the transaction 1 timestamp. So in a sense, transaction 1 is happening in transaction 2's future. Therefore, transaction 2 can just ignore whatever transaction 1's doing. They they are linearized, right? Transaction 2 happens, then transaction 1 happens as far as the system time is concerned. You can imagine also how that would happen. Like, imagine that there's actually a gateway server up here and up here, and those clocks are not going to be perfectly in sync. And so when that command comes through, that gateway server attaches a timestamp to that command. And so if transaction 2 happens to land on a slower node that has a slower clock, it may get a lower timestamp than transaction 1, right? It doesn't exactly map to wall clock time, which is the property that there's no universally coordinated time. Make sense? Question?
What happens if transaction 1 just stays in pending forever? Is there a cleanup job or something like that?
Right. So that would be the other case where another transaction comes along that has a higher timestamp than so there is a timeout on those transactions. They're not allowed to just stay open forever. But also when a transaction, if there's a different kind of conflict, which is that this transaction, basically this is not even a real conflict, right? What we showed here, like this guy figures out that there's a transaction here that has a higher timestamp, so it doesn't even care if it commits or aborts. It could just ignore it and read the value. But if it had a higher timestamp, it would need to do something about the other transaction. Either it would restart itself, which is a thing that happens in Cockroach when you have conflicts. So basically it would error back out to the client and say, sorry, there's somebody here with a lower timestamp than you. You better restart yourself at a higher timestamp so that, lower timestamp than you. You got to like move yourself up so that they may have committed or not. Or you basically abort the other guy. So you mark the other guy as aborted. When he goes to commit, he'll notice that he's been aborted and has had his timestamp ratcheted. Because you're also, you get what I'm saying? Like if a read comes in, it forces the write to then apply above that read so that the read has not been invalidated by that. Right. Cool.
An easy way to put it is if you have two TXNs and they both conflict, then either one or the other got to be aborted. Yeah. And depending on what your timestamp is, if you have a lower timestamp, the other guy typically gets aborted. Otherwise, you get aborted.
It usually doesn't actually depend on the timestamps decide whether or not there's a conflict. Once there is a conflict, there's a separate system of priorities that decides probabilistically which one gets aborted. So that gives you the property that you can do something like a analytics query or something if you need it to be like reading very recent data, can run with a low priority, which makes it very likely to be aborted in case there's other foreground queries running that have higher priority, like line of business queries. Right, so then that guy commits and off he goes. The other guy also commits and no conflict, basically. So we kind of talked about this already, but if we have a write conflict, they basically both try to write the same key. So the second guy comes along and like, this is definitely a conflict because they're conflicting timestamps. So this guy consults the transaction record, sees it's still running, wins the coin toss mechanism, and aborts the other guy, and then updates that intent, basically overwrites it, and then he's able to commit. And then the first guy, we don't need to show it there, but what will happen is the first guy will then try to commit, notice that he's aborted, report back to the client, and the client basically, the contract in Cockroach is that you run your transaction in a closure so that it can be rerun multiple times. So you kind of have to, don't send emails basically in that closure because it could run like arbitrary number of times essentially. But what will happen is essentially the client will start again. And like if that first transaction laid down like other intents that aren't related to this conflict, those intents get to be reused. So that kind of saves you a little bit on the performance of that retry.
Again, like another way to think about it is on your client, you have to do the same kind of thing that you would do to handle deadlock situations or connection drops or anything else where your transaction's interrupted. And so if you want to write really reliable code, you've got to, even with MySQL, you've got to be able to rerun your TXN.
Yeah, so, right, so these exact kind of things can happen. If you run Postgres and serializable, you will get these exact kinds of conflicts. We've actually talked about having a development mode in Cockroach where we like artificially inject these restarts at like 10-25% of the time so that it forces you to write your code in the right way. but we haven't done that yet.
How do you make sure that read writes transactions still give you serializable transaction isolation in the case you're reading some unrelated some data, for example, right? Like there should be presumably some locking that hasn't been covered here.
Right. So there's no like how do you observe a read write where the read arrives after or the write
Let's say I read
arrives after?
something and then I did a write that was to some other range that was dependent on that data, right? So what would prevent some other transaction from going out and changing it and like?
Right. You're saying that you read something and then a conflicting write arrives later in wall clock time, but with an earlier timestamp. Yeah. So there's no locking. What happens there is that there's an in-memory data structure called the timestamp cache that keeps track of exactly those reads. Like it keeps track of when was this key last accessed.
Does it effectively give you the lock contract? Like you'll start.
Yeah.
Okay.
Yeah. The reason we can do that is because we have what we call leader leases. So there's essentially always one replica that all reads and writes go through for each consensus group. And therefore you can maintain this in-memory structure. And it has
So
a
it's
low
an in-memory lock. It's
sure.
still
Yeah.
there.
Cool. So like I said, a bunch of detail here is omitted, but the gist of it is that we bootstrap transaction atomicity on single key atomicity that we get from using Raft for and there's a great blog post, and I'll shout out to the blog a couple more times that has more detail on this stuff if you guys are interested.
Where is the transaction record written? Is it in follower or leader? Like
Say that again.
transaction record, where is it written before it starts?
The transaction record is like any other key. It is replicated to the entire group. So it basically, from the perspective of the consensus group, is like any other operation. Cool. Any other questions before we move on? Yeah.
Back on replication, I was thinking that you said there's one consensus group per 64 meg shard. And so let's just multiply that out. Does that mean that for like a terabyte of data, you'd have something like 16,000 consensus groups?
I'm not going to check your math, but yes. Right.
Yeah, but on that order of magnitude.
Sure. Yeah. So one thing to know about Raft is that it's a pretty chatty protocol. There's all these heartbeats flying around, and those can be pretty inefficient, particularly if you can imagine exactly that, right? Imagine that you have a cluster of just 3 nodes, 16,000 consensus groups, but they're all co-located on the same machines. You would have O of 16,000 heartbeats flying around, even though there's only 3 machines.
Right.
So this is one of those things that's actually not covered in the Raft paper, for instance. What we do is we implement coalesce heartbeats. So we basically buffer up in memory a couple heartbeats, and then, okay, these are all going to the same machine. We can condense these down into one message and send that off as a single heartbeat instead of 16,000 of them. That's one technique that we use to minimize that background chatter. Another technique is if a range is not active, it's been sitting there and hasn't had any activity for a while, we quiesce it, which means we basically just sort of make it dormant until the next command that comes along wakes it up.
Okay.
You had mentioned earlier there was like a 5-minute heuristic right now on network partition or something like that. Is there something that does ongoing consistency checks on ranges and replications? Say you have a 2-minute dropout, right? Is there something that's going to check and repair the data on that replica?
Okay, so there's 2 ways to interpret that question. I'll answer both. So the first, my first interpretation is what notices that a node has gone away. That is the responsibility of each consensus group. It does, so there's no centralized authority that does that. Each consensus group knows how many, so as I mentioned earlier, we have this notion of read leases or leader leases. And so there's one of those per consensus group, regardless of its size. And so that thing has a background worker that will check, okay, I need to have 3 replicas, but hey, I only have 2. So I better look for a candidate and sort of up-replicate myself to that. That's not a consistency check, though. We also have a thing that runs in the background that, as a Raft, sort of puts into Raft this. So the leader will take and basically hash all of its local data and send that hash into Raft. And when that command comes out of Raft and gets applied on the followers, they will hash their local data and compare to that hash. If it's a match, all good. If not, there's another graph command that happens that will actually generate the diff and typically like crash the guy who doesn't agree with his two friends.
That's not expected to happen, right? Or is it?
It's not expected to happen, but there's definitely been bugs that we found this way in our testing clusters.
How are the consensus group sizes configured? Is it all dynamic? And if it is, how does it downscale? To say like, oh, let's ditch this half the cluster for whatever reason.
Okay, so the way that so where is the configuration held?
Yeah, it says, let's say, it start with 10 nodes, grow all the way up to 21 nodes. Now the consensus is 9 nodes. Then it downscale back to 10 nodes.
Oh, I see.
How
you're
long
talking
before
about-
they realize that they are no longer a cluster of 21, they are now a cluster of 10?
Okay, so so one correction is it won't be nodes, it'll be replicas.
Okay.
Right, because the number of nodes in the cluster is kind of irrelevant for that.
Okay.
The configuration that controls how many replicas a range will have is again just some key that lives somewhere in that map, in that key space. And so you basically, I think you updated, there's actually a SQL interface. It's like a SQL table that you write to, and that's a special system table. That propagates through the cluster using gossip, which I haven't talked about, but there is a gossip protocol that sort of is eventually consistent, and we use that to propagate things like that. And then again, the leaseholder will observe that the current configuration of a range doesn't match the prescribed configuration, and sort of one at a time take actions to sort of converge those two again. So it will probably pick a replica which is located on a node that has higher disk utilization or something than some of the others, and drop a replica from there until it's in balance. Cool. Okay. All right. So I'm gonna assume there's no more questions. Cool. All right. So to understand how we map SQL operations at a very high level to the key value thing underneath, just a quick primer on KB primitives that we have in Cockroach. So you can get a key and you get back bytes. You can do a conditional put that will fail if the value is not what you expect it to be. You can do a scan, and you can do a delete, and there's more operations, but these are enough sort of to understand to the extent that we're going to talk about it. So in Cockroach, all tables have a primary key. We actually do support tables without a primary key, but we will just create one for you and won't tell you about it. It used to be that there was one key value pair per column or per cell, but you can see why that might be inefficient, because it means that if you're inserting a row, you have O of columns rights. So currently, by default, we create a single column family that contains. So we have this notion of column families where you can configure which columns get written together as a single key in the key value store. So if you have like a table that's very wide, something like hedge, just because that's what I remember, but you know that you like write half of them at one time and the other half at another time, you can use two column families so that those are both like single writes. The trade-off, of course, is that if you update like one of those columns instead of the whole family, you're reading out the whole thing, making one little change, and then writing out the whole thing, even though you only need to change one column. So that's like a knob you can do. And then what the keys generally look like, those slashes are they're not real slashes, but it's pretty close. Like remember the keys in Cockroach are just runs of bytes. So there's like some delimiter followed by the table identifier, followed by the index identifier, followed by the actual key in that index, followed by the column identifier. So I'll show what that actually looks like. So let's say we have this table, very simple one with no indexes except for the primary, an integer ID, and some columns, and we're gonna insert a row into it. So given that that's our key anatomy, we have sort of the table name test, the index identifier is primary, and the value of the key. This is basically the primary key. So see how there's a 1 up there? That's our primary key. So the ID is 1, and then the column identifier, name, price. Those are shown here as text, but in actual in the actual implementation, those are just like integers, basically column IDs instead of full-on names. Cool. Oh, and then one thing to note is that at the level of storage, which we haven't talked about at all, we use RocksDB, which will do prefix compression. So you don't end up encoding the whole might be very long key every time. RocksDB internally will do prefix compression, so you don't pay that overhead on every key. Does that make sense? So adding another row, very much the same. And so you can imagine, like if we wanted to do a secondary index, we would have like test slash, like primary is basically 0, and then we would have another index that would have ID 1, and that will have like whatever value you want. So maybe it's the concatenation of those two other columns, and we like concatenate those two and encode them into the key. And so that will give you efficient point lookups into that secondary index. And the value of that secondary index will be the primary key of the row. So in Cockroach, when you query through a secondary index, you consult the secondary index to find the primary key, and then you go to the primary key to find the rest of the row. Again, there's a blog post on how this stuff works. There's some pretty interesting optimizations, like you can do an index. Like let's say you know that when you query on a particular index, you are interested in the values of certain columns. You can do a containing index, which encodes in its value not just the primary key, but also some other set of columns that so that it could save you that second indirection into the primary key. So you trade away some write throughput for better read performance. That make sense? Cool. Cool. Yeah, so like I said, there's a blog post, more detail, but this is basically all I'm going to talk about SQL. Any questions on that?
You're going to talk about how to execute SQL, do SQL query planning? Or...
No, my knowledge of that is probably a little stale about how that works now. In general, the early implementation basically would do everything on a single node and sort of be very inefficient in terms of data locality. So a lot of work is going into distributed SQL now, where we're moving the computations where the data is. And so typically when new functionality is being added, it'll be implemented in like local SQL first because it's easier to write, and then as we go, we're backfilling distributed SQL. That's like a big area of focus for 1.1.
So is it fair to say that so I'm totally ignorant, but for Cockroach 1.0, it's basically the key value part is the stable and like really a nailed thing. The SQL layer is kind of later on, or
I don't think I would characterize it that way. The SQL layer inherently is like much simpler and has fewer like catastrophic bugs.
interesting.
Yeah,
Curious as to why.
just because most of the performance work ends up happening in the key value layer, and that's where there's a little bit more churn there and a little bit more. It's much more subtle. It's just inherently a little bit more difficult to work in, and so.
Yeah, I think it's also fair to say that the optimizer 1.0,
There is no optimizer,
right?
Yeah,
Exactly.
there is no
It's extremely
optimizer.
primitive.
Yes.
And therefore it's
Right.
simple, which means that there's less to go around.
Yeah, exactly. Yeah. So as
I think it's a rich space of problems.
right. Yeah. So it is worth noting that the optimizer is non-existent. So if you write your join in such a way that the big table you're joining to a smaller table happens to be on the wrong side of where our implementation buffers one of those in memory. So you're trying to buffer in memory like the big one, and then you're like streaming through the small one, it will perform very badly. And if you flip that join, it will perform much better. So currently the system doesn't do those transformations for you. But that is, again, an area of active development.
Tack on with that, like if you were actually pushing like an explain query or something, does it just show you like the list of like key value store commands that would actually be executed?
Yes, there's an explain debug. Actually, I think we have time, so I'll probably do a little demo and we can actually just run through some of these examples.
Well, you got about 3 minutes.
Oh, really?
Oh, man. Really flying by. You're right.
Okay.
But some may be able to stay a little later.
Yeah, all right. We'll do that as an reference. So yeah, so quick deployment. So we're mildly obsessive about not having any external dependencies. So it's just like one binary. I'll try and show some of that, but there's no special nodes. When I talked about gateway nodes earlier, those are just normal Cockroach nodes. You can just, when you want to have a client talk to something in the cluster, you can point it at any Cockroach node and it will like automatically route to the right store that has data on it. All buzzwords. So yeah, so where we're at now. So we released 1.0 like in May, and 1.02 is like currently baking on our testing clusters. So it'll probably hit like homebrew and those things in a couple days. Yeah, so we've sort of declared that it's production ready, but like it's really production testing ready. So please don't put production data on it, is my opinion. But do test it. Like we've had a lot of sort of companies engage with us and give us useful feedback for what they care about and what like weird bugs they hit that we just haven't uncovered in our testing. And so always useful to have people like chime in. Yeah, so but we already have like pretty robust ORM support, so you can basically I'll show this, take a Cockroach database, like start it up, take a Postgres client and just like talk to it, and it just kind of works. And we even went through a lot of pain to support a lot of the Postgres specific like reflection facilities and stuff to make things like Active Record and other like crazy ORMs work. Yeah. Cool. So we made it. Thanks for coming. I have if anybody has more questions, I'll take them now, and if people can stick around, I'll do a little demo and play around. So the question was why the name. Got this question a nauseating number of times. I don't know. I like the name. It to me like the emotion that the emotional response it creates in me is that it's like robust and resilient and like hard to kill. It's like oddly made me like not be so grossed out about actual cockroaches running around. But also like who cares? It's a name and it's very memorable. It's actually been a successful name in that regard. In my opinion, it's fantastically successful.
The whole point that cockroaches are going to survive nuclear war.
Yeah, that was the
Will
original
your
idea.
database survive
Yeah, but there's like
nuclear
all these
war?
other databases out there like VaultDB, VaultDB, Couch, and I don't like nobody can remember all these, but Cockroach nobody forgets.
It's a bold claim.
All true so far. Cool. All right. So yeah, feel free to take out we got two, and I'll do the demo thing. Okay. So, yeah, I can see you too. Thank you. Hey. Come on, Marty. Congratulations.
Oh, yes, they're happy.
I'm laughing at you.
Yeah, you never forget.
Yeah.
I saw you last weekend.
Oh, cool.
Yeah.
I was sick that day, so
Oh, you were. Yeah.
they were so